Hello. So, welcome again to module 3 where we were discussing different numerical ways of solving linear equations. In the previous lectures of the modules we covered what is known as the direct method for solving the linear equations. The direct methods that we considered included Gauss elimination method, Gauss-Jordan method, the LU decomposition method, and we also covered basically a tridiagonal matrix algorithm which is specific to a special type of tridiagonal matrices. As opposed to this direct methods, the quality of the direct methods that we looked at essentially was that when you get set of equations and we solve these set of equations, provided we do not have any round off errors, the results that we are going to get are going to be exactly accurate. Okay, so that's and the reason why they are called direct methods is because once you get the solution, you have the solution, we do not iterate over the solution multiple number of times. As opposed to the direct method, there is another class of methods known as iterative methods. For solving linear equations, and we will basically be covering the iterative methods in this part of the lectures. Okay, so the examples of iterative method, the first example that we will start off with is known as the Gauss-Seidel method. Okay, and I will take a relatively simple example of two equations in two variables, and actually I will show you how the Gauss-Seidel method works. Under certain situations how the Gauss-Seidel method does not work, what we need to ensure in order to say that the Gauss-Seidel method we can get it to work, and we will look at essentially how to analyze the results that we get from the Gauss-Seidel method. So the simple example that we are going to talk about again is basically going to be x plus 2y let us say equal to 1 and x minus y equal to 4. So the solution for these two equations we know is 3 comma minus 1, that is the solution. Okay, and we can solve it in a fairly straightforward manner using Gauss elimination method. What we will see now is how to use the Gauss-Seidel method. What we do in Gauss-Seidel method is rearrange this equation so that we write it in terms of x equal to something to the right hand side. We rearrange this equation so that it becomes y equal to something to the right hand side. Okay, and two possible ways of rearranging this equation are fairly clear. So you can take 2y onto the other side and you can write x equal to 1 minus 2y, and the second equation you can write this as y equal to x minus 4y. Okay. So what we have done is we have used the first equation to express the overall result in terms of x, we have used the second equation in order to express the overall result in terms of y. So that is one way of rearranging these equations. The second way of rearranging these equations is to use this equation to obtain x. So we will write the second equation as x equal to 4 plus y, and the first equation we will write that as y equal to 1 minus x divided by 2. Okay. So the first step, as we have said, we have done nothing but just rearrange these equations such that we have the unknown variables to the left hand side and we have what we will for the time being considered as known variables to the right hand side. Now it is an iterative procedure, so what we will do is we will start with an initial guess. Okay, x superscript 0, y superscript 0 I represent superscript in the bracket in order to say this is the initial value, the 0 represents this is the initial value, and as we iterate multiple number of times, this particular coefficient will become x1 y1 x2 y2 x3 y3 so on and so forth. Okay. So we use these rearranged equations as an update equation in order to improve the value of x and y. So let us look at if we use the first equation. In that case we will write x I plus 1 equal to 1 minus 2y, the value at the ith equation, and then the second equation we will write this as y I plus 1 equal to x I plus 1 minus 4. Okay. So these are the two equations now we are going to use. Notice what we have done is in the equation for x we have used the value, the previous value of yi. In the equation of y we have used the newest value of x. So what we do essentially in a Gauss-Seidel iteration is use the latest values of x and y that we have computed through the iterative process. Okay, and we will start with some value, and let us say we will, just for convenience sake, we will start with origin. Okay. So we start with origin and use these equations in order to find out the new solutions of x. So let us say now what happens at iteration number 1. Or rather I should say at I equal to 0, what we get is x1 equal to 1 minus 2 times y0, which means basically our x1 is going to be equal to 1, and we substitute that value 1 in this particular equation, and y1 we are going to get is 1 minus 4, that is equal to minus 3. Okay. And at this point of time what you can do is just try to basically solve these equations in order to get x2, x3, x4, x5 and so on, and we will keep doing that. So we will substitute the value y equal to minus 3 in this equation, so this becomes 1 plus 6, so x2 becomes 7, y2 when we substitute that value in this particular equation, y2 will get the value of 3. Okay. Now what we do is we iterate on this again, x3 is essentially going to be 1 minus 6, that will end up being minus 5, and essentially y3 will end up being minus 5 minus 4, that is going to be equal to minus 9. Okay. And we continue doing this over and over again, and we will find that this particular solution does not converge to the desired to the actual solution x equal to 3 and y equal to minus 1. So we keep on repeating the process, and we will find basically that x is going to go to minus infinity or plus infinity, and y is also going to go quickly diverge to plus or minus infinity. Okay. So that is what if we naively use equation the form 1 in that is this particular equation is recast in this form and this particular equation is recast in this form. Okay, I actually made an error over here, so we will have y equal to x minus 4 and not x minus 4y. Okay. So if this particular form is used, what we see is that we are not converging to the desired solution. Let us use the second form of this equation, and the second form essentially was x equal to 4 plus y and y was equal to 1 minus x divided by 2. We started off with x0 equal to 0, y0 equal to 0. Okay. So, we substitute y0 in this particular equation, we will get x1 equal to 4 plus 0, that is 4, y1 is going to be 1 minus 4, that is negative 3 divided by 2, that is minus 1.5. Okay. Then we substitute minus 1.5 in this equation, and x2 we will get x2 as nothing but 4 minus 1.5, that is 2.5, y2 is going to be nothing but 1 minus 2.5, that is minus 1.5 divided by 2, which is minus 0.75. x3, we continue this, we substitute y2 into this equation, that is 4 minus 0.75, we will end up getting this as 3.25, and y3 is going to be 1 minus 3.25, that is minus 2.25 divided by 2, that is minus 1.125, and we continue doing this until a long enough time, and we will get our solution of x3 equal to 3 and xn equal to 3 and yn equal to minus 1, where n we choose as large enough such that the results that we get we say are converge. So, what is the stopping criteria that we are going to use? The stopping criteria, keep in mind that essentially we do not know a priori what the solution is. For this particular example, yes, we do know that the solution is 3 comma minus 1, but in general we do not know what the actual solution is. So, what we have to do is we have to compare the solution xn with xn minus 1 divided by xn minus 1. This was our approximation error, and we do that for all of the variables, and if this value turns out to be less than some tolerance value that we specify, at that particular condition we say that our overall iterations have converged. For example, in this case x0 has changed from 0 to 4, that is a pretty large change that we observe. In this case it has changed from 4 to 2.5, so the change is actually 1.5 divided by 4, so that is a pretty large percentage of change, almost 35% change when you go from 4 to 2.5. Likewise, from 2.5 you are going to 3.25, that is also a pretty large change. After a certain point we will see that xn minus 1 and xn and so on and so forth, they will start differing from each other with relatively small amounts, and when that difference falls to below epsilon tolerance, at that time we say that the overall Gauss-Seidel iterations have converged.